ahead for family members to say, you know, what they would get out of this. And so I think the previous talk has said a lot of stuff that I would have said anyway, which is fantastic. And essentially, population synthesis is answering a few questions on, statistically answering questions on how do stars function, how many of each type of star are there, and actually some of the challenges we have coming up in the next few years, I think, are really just big statistical questions. As other people here have mentioned, I'll touch on that a little bit today, but obviously I can't go in much detail, but I can give you a little bit of what we do. And I say my hair is still that long, it's falling out, but you know, it's still there. So the reason that population synthesis is so important and why the numbers of all these different types of stars is so important is because of the big data. And we now have so many constraints. We have DR3 from Gaia came out today. I haven't had a chance to look at it, but if anyone's watching anybody on Twitter, you see endless tweets of people saying they've already done all this stuff. So this stuff is coming fast. We've got the black hole mergers, the neutron star mergers, all this stuff is coming in the future, and there's lots more to come. So how can we use this data to constrain our, in my case, what I'm interested in are stellar models, and in the previous talk, you see that relates also to galactic chemical evolution models. So I'll give you an idea of what we do on a day-to-day level that's very simplistic, population synthesis. So this is essentially stellar accountancy. It's not accountancy because they get paid well and we don't, but at least in this case, we are looking at how many stars we can make. And I'm going through this, I'm sorry about putting an equation here. It's not a hard one. It's very simple, but this shows you all the stuff that we need to put into the models and how it connects to what you are doing. So the first thing we're going to do is count stars. So that's n. N is the number of stars. It's very easy. So let's count that. And the first thing that goes in here is the star formation rate. Now, we haven't seen much, I think, this week on star formation rates. This is something, of course, goes into the chemical evolution models. I should say, for what we do most of the time, just looking at, say, the solar neighborhood or just looking at very old populations, which I've done recently in the galactic bulge, we can treat it as a constant over a fixed time, and that's not such a bad approximation. You can see in these plots here, you can see that for some of these external galaxies, and this is old data, there's much newer stuff out there now, but I like the colors on these plots. You can see the constant star formation rate. It's not a terrible approximation. So, you know, if you see a lot of papers that do that, for some galaxies it works. But you see for others like Sculptor, apparently it doesn't work. So we have to be careful. But that's what we need. That's some input that we need to go into these models. We also need this generation function. What do I mean by a generation function? This is how many stars are born of each type. And the simplest way to think of this is the initial mass function. Anyone that studied astrophysics knows about this function. It's a very steep function of the mass. So you have many low mass stars that essentially do nothing except swallow up the mass as far as chemical evolution is concerned. But then you also need to know how many of these high mass stars do we have? And I've plotted here, this is from quite a while ago, but there are many papers out there trying to estimate this, and they all give quite different answers. And one of the goals in what we do is to try to say to you, okay, if we have a population made with this initial mass function, what are the uncertainties? And I think the uncertainties here, you know, factors of 10. So issues already if you work with massive stars. And I should say what I do in particular is to work with binaries, and binaries really make your life complicated because what would have been a one-dimensional parameter space now is instantly a three-dimensional parameter space, possibly more. We can say, okay, all binaries are the same metallicity, they're all the same eccentricity, say 0 because that's simplest, and then you're down to still having the mass and the secondary mass, the other star, and the orbital period, or by Kepler's law, the separation. And that's all well and good. And we actually have, and from some more modern data from the solar neighborhood, from Mo and De Stefano, they did a fantastic study of putting together many other studies and calculating what the effects of the selection functions were. And they have now actually said, well, okay, we can tell you what the function is, what this function psi is in the solar neighborhood. They can also tell you how many binaries there are. And we see this plot here. This is just the primary mass on the axis down here on the x-axis, and the number of systems is on the y-axis. And you see for the sun, which is around here, mostly they're single stars. We knew that, that's fine. But as soon as you get up to a few solar masses, the number of single and binaries is the same. And as you get up to a few tens of solar masses, the number of triples, that's the blue line, and quadruples, which is the purple line, those suddenly become very important indeed. And that is something that we're working on, and there are other groups working on it as well, and I think is something we should consider in the future. And the final bit of very important stuff in here is the stellar evolution. And that's this function here, which I've just called delta. If you're just counting stars, you just need to know whether the star is one that you are interested in or if it's not. And that's very simple to do. You just say delta is 1 if it's your star and 0 otherwise. So if you're counting red giants, on the time step that it's a red giant, it's just 1. I told you it was a simple equation to calculate. You add this up over all of your stars. That's this sum I here. And then you have your number of stars. I've greatly simplified this, of course. Now, this workshop is all about looking at the problems we have and how we may address those problems. And in this case, one of our problems is the input parameter space is very large. I mentioned that for binaries, but if you go up to, say, quadruples, you've got four stars, you've got 3 separations, 3 eccentricities, 3 inclinations of these orbits. You also have issues with the rotation rates of these stars. I mean, I'm talking the birth rotation rates here. And many of these distributions are either poorly known, and maybe I'm being polite when I say poorly, we just don't know for many of them. And then even if you know these, there are things that are uncertain in even normal single star models, and also in binaries you have issues, such as mass loss rates, you don't know that. Mixing in stars, there's a lot of uncertainty, particularly rotational mixing. Nuclear reaction rates have been touched on this week a lot, so I refer to others for that. But if you look at binaries, we have the mass transfer efficiency. We don't know how much mass is actually transferred and how much is lost. Common envelope evolution remains a problem. Our efforts to model it are improving, but it's still very, very much an uncertainty. What happens when stars merge? What happens when you kick them in supernovae and things like this? These are all still, I think, very big problems. Now, one of the other practical problems we have is that often you need a lot of stars in your simulation in order to find the stars you're looking for. If you're looking for, say, black hole mergers, they're actually quite rare, and they're rare because you have 2 supernovae which both want to break up the system. So you're looking for the very few systems that don't go through that breakup channel. And also stellar evolution codes are a real pain in this regard because they're not that quick. They take hours to run, possibly even longer if you're doing, say, thermally pulsing stars. And they may not even model the stars that you want. And they tend to do this thing called crash, which is not good. So if you want to model 1 million stars, they're not actually that reliable. So you have to pre-calculate. So what we do is we offload a lot of this stellar evolution to what we call these synthetic codes. Because we have 1 million stars, say you want 1 million binaries, you want to do this in a practical timescale. And so what we do is we develop grids of models, or in the old days, and people still use it because it's reliable, we have analytic function fits to model properties. These replace the slow stellar evolution calculations, but they are good enough for what we do. And usually, they're accurate to 5%. That's, for most things, that's accurate enough. So we can do about 1 million stars on my desktop in much less than 24 hours at the moment, which is pretty good. And that's with all the full nuclear synthesis, which I'll come to in a minute. Now, I should say before we go any further, having public and open source codes and data really helps us in this desire to build these analytic or grid-based models. So thank you to everyone that does things like that, like the MESA crew and people like that. That's really great. So there's a load of these codes out there. I just wanted to mention them because otherwise, they won't buy me a drink at the bar. And these guys haven't either, but maybe next time. Many of them are based on this library called SSE, Single Star Evolution, or BSE, which is not mad cow disease, but it's actually binary star evolution. And the code I run is also based on this, and there are many others that you will see out there. So we already saw some of the Star Trek stuff in the previous talk, but there are many others. And some new ones have been developed recently. Mostly these are people who are trying to do neutron star, or neutron star black hole merger type simulations. There are also people trying to combine detailed codes like MESA with the BSE code. So when you need the detailed code, you can grab it and do all your detailed physics in there and then switch back to the quick code when you don't need it, which I think is a very smart way of doing things. So we had a review paper on this. I'd refer you to that. It's got a table so you can go look up all these codes, and they're all fantastic. So Now, to give you an idea of the kind of things we predict, this is something that my BSc student, my bachelor student last summer cooked up. That shows you how easy it is these days. We can make, for example, black hole merger rates as a function of time. This is for a starburst population at time 0. So we can make these predictions. She did it for 2 different initial mass functions. That just shows we can then say what the error bar is here. And it's spiky because it's low resolution we were testing, but you can make it as flat as you like. Going back to the chemical evolution stuff, this is stuff I did, well, this is essentially 20 years old, but we've updated all the physics since. We've had chemical evolution predictions since then of, I think I've got about 400 and something isotopes that I'm now generating. This is carbon-12, which is very common, but there are many, many others out there. So I can tell you the rate of mass lost as a function of time from a starburst for any of those isotopes. And this is for single stars and for binaries. And so it's a combined population. And I can do this for all of the isotopes. So, very, very handy stuff, but it's a lot of data. So you've got to be ready to handle it. We can predict things like type 1a supernova rates. This is from Jokic Klaas's work some years ago, but we do the same thing now. So you can make those predictions. You can also compare to observations, which is something absolutely essential. I've been doing this a bit more recently for old galactic bulge stars. So these are, here I'm showing a carbon to nitrogen ratio as a function of stellar mass in the bulge. So these should all be very old stars. They should all be around 1 solar mass. And you see they are roughly around 1 solar mass. But all these stars to the right of around 1.2 solar mass shouldn't exist. So that was a problem. But if you have them in binaries, they naturally exist. And the colors here you see are, the red especially, these are merged stars. So this is the masses we expect from merged stars. And the C/N you can predict from the stellar models. And so we can quite happily produce as many of those as we want from the merged stars. They explain that quite well. So we can compare 2 observations, but I have to say, just comparing by eye, this kind of thing is not the way we want to do it in the future. We already use Bayesian type methods to compare observations to models. We can do it 1 star at a time. For example, this is the Bonsai code. There are others. Bonsai is very good. They use whole grids of models, and they given here, for example, this Sagittarius A, we can say what is the best model fit to the luminosity, effective temperature, and the gravity, for example, and get from that a mass and an age. With uncertainties. So we can do it star by star. It's more difficult to do it for a population, but the group in Birmingham, or I think have now moved to Australia, they're working on this. They've done a lot of stuff with Bayesian predictions with multiple parameters. Here you've got 4 parameters. And the problem is that if you have 100 parameters, and indeed my model I think has 200 or so parameters in it, it's very difficult. So that's a bit of an issue. But I'm hoping that people here can help with this. I've seen a lot of stuff from nuclear physics, which I think is very applicable to this.
1 minute.
Yep. And then just to give you an idea of what else we can do, we can predict what is observable. So this is things in the future that may want to be observed. So here is a prediction done this year by Evans et al. They tried to see whether hypervelocity stars, that's stars that are ejected from the galaxy at a certain speed, could actually be made with the models. And they found the only model that matched some of the stars observed is what they call the optimized model. So they turn all the knobs up and they get it that way. So it's very unlikely that this is real. And this one is just for Sumner. So you can see we can also predict nova properties in these stars. We can predict properties of any of the stars we expect to explode, which is it's all very useful. This is Alex Kemp's work. He's a guy at Monash who's doing some great work on this. So we can give you that. So if we can use the models of the novae, we can put them in here. Now, I just wanted to say one last thing before we go. I've heard many times over the years that you can get what you want from these models. By turning all the knobs any way you want, you can get what you want. That's not true anymore. That may have been true once. It's certainly not true now. We have such good constraints on many, many things, especially with Gaia. We have wonderful constraints on the birth properties of these stars now. If we give big error bars, that's because we don't know. It's just us being honest. And most of the uncertainties we have also exist when you do stellar evolution from using a detailed code or something like that. So these uncertainties are there. But I should say it's not that bad because most of the parameters in our model don't matter for whatever star you want to look at. So if you only want to look at merged stars, then some things like the wind mass loss rate probably doesn't matter too much. So that's not too bad. And I would say to the people who are making models, many of our parameter spaces, such as if we put in, say, nova models, I mean, if we use Sumner's work, he had I think it was one solar mass. I'm sorry if I got that wrong. It was one model with one mass. The problem is our novae that we make are a variety of masses at a variety of accretion rates. And so what we need is to cover that parameter space. And I know that's difficult, particularly for explosion models. But of course, our models are only as good as the models we put into them. So please do not use population synthesis models as black boxes. You have to understand what's going on. So let's finish there. I mean, I think population synthesis is a very valuable tool, and it links the stellar and nuclear astro all the way through to the observations. It's great. And you can put these in chemical evolution codes. It's very simple. I was doing it 20 years ago in my PhD. It's very easy. The problem is that even though we can constrain many, many parameters and combinations of parameters, we still have needs, and some of these needs are stellar evolution data. Please make that public so we can use it. If I knew where to get a good set of, say, neutron star merger R process yields that was public, I could put it in my models tomorrow. It would be fantastic. We also need stellar interaction models, say for binaries, triples, quadruples. The input distributions, I think we need them outside the solar neighborhood. It's going to be really hard. Selection effects I haven't touched on.